Right, can you see the slides? Okay, all right, so let's get started. Let's move on to magnetron sputtering. We've discussed about sputtering, and magnetron sputtering is one what we call one setting or one hardware that you can add into the sputtering process in order to increase the deposition rate. So that's called magnetron. In conventional DC and RF, efficiency of ionization that we have from the plasma accretion of the argon is usually low. So if the ionization is low, that means the sputtering rate will be low as well, or it will translate into low deposition rate of the sputtering. So in order for us to enhance the deposition rate or the sputtering rate during the process, we can use a hardware that we call a magnetron. Okay, it's called magnetron. So what is a magnetron? Magnetron is a piece of hardware that you put behind the sputtering target in order to focus in order to concentrate more electrons and enhance deposition rate, enhance incident rate of the plasma with the target material in order to create more deposition. Right, if you look at this, the first 3 points, most electrons lose their energy in non-ionizing collisions. So this is what happens in typical conditions. So few argon atoms are converted to positive ions and few positive ions strike the target. So since we only have few ions striking on the target, we're going to have low deposition rate or low sputtering rate. So with a magnetron, what we have, you can see on the right hand side here, the illustration. Magnets are used to increase the percentage of electrons that take part in the ionization event. So we concentrate electrons in the front of the target in order to enhance the ionization process, therefore enhancing the sputtering process. So you have electrode here on the right hand side, and then we have a magnet to concentrate the electrons in the front. So we normally put our target in the front of the magnetron. So then electrons and the gas will be sort of accumulated in the front of the target material, enhancing the deposition process. The field is applied at the right angles to the electric field by placing large rectangular magnets behind the target. So you're going to have your target in the front, and then at the back you're going to have a magnetron. So you literally have magnetic fields around the target from the behind, and then it's going to concentrate the electron and the argon gas in the front in order to ionize more, and therefore creating more and more deposition. So this results in more deposition, a high deposition rate if you compare to a system without a magnetron. Right, so this is how it looks like. So what it does is it traps electrons near the target surface on the front. So by concentrating the electrons in the front, causing the electrons to move in spiral motion, more or less following the direction of magnetic fields until they collide with an argon atom from the gas injected in order to induce ionization of gas. Ionization and sputtering efficiencies are increased ion density of around 0.03% compared to 0.01. So this shows increased percentage in comparison to a system without magnetron. So you can also manipulate in this system argon pressure in order to produce better film quality. Usually, if you talk about argon pressure, if you go for higher argon pressure or higher gas pressure, you typically end up with thin films with higher roughness. So on the other hand, if you go for lower pressure, then you normally end up with film with lower roughness. So if you talk about, for example, if you talk about roughness of the films, how do we measure the roughness of a surface? Thin films or wafers or glass? How do you measure? From your previous FYP experience, how do you measure the roughness? Anyone would like to share? How do you measure the roughness last time? Anyone did roughness measurement? Hazika, did you do any roughness measurement last time? Hazika? Amira? Okay, no, just look at the surface. Use FISAM, right? Use FISAM. So, but using FISAM, we don't get the value of roughness, right? You can see the roughness by your eyes qualitatively, but there's no figure to represent roughness. Then what is a better characterization that you can use to see the roughness? Yes, AFM, atomic force microscope, right? So you can use AFM to measure RMS roughness of your surface. RMS is root mean square. Root. It's just an equation to measure roughness. So RMS roughness, right? So you can use RMS, for example, to compare the roughness of your sample at higher pressure and lower argon pressure. So planar and cylindrical magnetron systems available. So you can use planar system, you can use cylindrical system to incorporate magnetron into your system. So for example, if you look at this one on the right hand side, far right near the arrow, so you can see the pole of the magnet that we use here, north, south, right? So you can then design the concentration of the field around the target material. So over time, when you have magnetron used in your system, for example, use this sort of concentration or magnetic field design, you're going to see your target material eroded. For example, like this. Kalau you tengok target material, you can see from the top. Usually, it's in our lab. For example, it's a 3-inch diameter target. So over time, due to the use of magnetron in the system, you can go to the target and you can see from the cross section just using your naked eyes. Then you can see that dia punya tengah tu is actually eroded a little bit. Dia ada macam longkang dekat tengah, just like what you can see on this image, right? So it's due to the concentration of the fields by the magnetron during the deposition, which caused these areas to be spotted more than other areas on the target. So when you have the fields concentrating electrons, therefore concentrating more ionization of argon gas and therefore deposition at that particular locations in the middle there. So you're going to see more of the atoms being spotted off the target material. So dia makan kat situ lah, macam kalau you drive kereta, you dia punya bunga tayar makan sebelah stuff like that. So pretty much like that. So it's due to the use of magnetron in the system. You can go back to the, for example, if you get to do your internship in sputtering process or thin film deposition process department, later on you can see how the target erosion evolve over time. So another representation of the magnetron, okay. So dia punya magnet kat sini kat belakang. So this front side here, the eroded part is the target material. So this is all your target material. For example, ITO. Okay. So that's the eroded part there, the center, due to the concentration of the deposition over there, which indicates the presence of magnetic field around the areas. Okay. So this is how it looks like, lab scale system, sputtering system. If you've never seen such a system, typically this is how it looks like for a lab. This is industrial scale. So this is the system that we used in Fuji Electric last time to do hard disk drive deposition. Hard disk drive. So we did deposition on aluminium, I think 2.5 inch, 2.5 inch aluminium or glass disc. So it has 20 chambers in series, 2 stacks. One row is on the up on the top area, and another row is on the bottom area. So you have like 10 sputter chambers at the bottom, 10 sputter chambers at the top, and below here is all the electronic system, controllers and stuff. So magnetron will be somewhere there, right on the top area. So you have two tiers to do the deposition. So this is particularly for hard disk drive industry. So 20 chamber. So you just imagine the process, 20 chambers. That means step 1 will be deposition 1 done, chamber 2, chamber 3. Because kita punya hard disk drive, if you kalau you punya hard disk drive rosak, you can just try to open the drive. Nanti you akan jumpa finally a disk inside. A disk, either aluminium or glass disk. So that is, if you see the glass disk, you bring, for example, the disk under FESAM, you do cross section from the side, you akan nampak 20 different layers on the disk in order to enable storage of data on the disk. So that's why today we have like 1 terabyte, 2 terabyte, blah blah blah. So it's based on at least 20 different magnetic layers on the disk, enabled by this sputtering process. So kalau you tengok IC fabrication, for example, we have like various processes to do various stuff. Tapi if you look at HD industry, it's not semiconductor though, tapi it's thin film deposition based. The main processes are just in the sputtering. So you can have your glass disc or aluminium disc with the layers just by sputtering process alone. There's no lithography, there's no implantation, there's no diffusion, nothing else. Just glass cleaning in the earlier part of the process flow, and then you're gonna have like sputtering, sampailah dia build the HDD drive system with a needle to read and write and stuff like that. But the core thing in the hard disk drive is in the sputtering processes, 20 chambers. Okay, you can search later on how the process flow of HDD industry looks like, right? Kalau you nak pergi interview Fuji Electric, for example, ataupun last time we used to have now I think no more, right? So I nak interview Fuji Electric, for example, then particularly for media. So Fuji ni ada dua main business domains. One is FEM, Fuji Electric Media. Media means HDD industry. Another one is called FSM, Fuji Semiconductor Manufacturing. So they just plant belah-belah je dekat Kuala Lumpur. So I was in R&D of media last time doing sputtering. So the other one is like IGBT semiconductor kind of thing, which involve fabrication processes that we learn all this while, right? That's just another industry. So biasing, you can apply biasing during sputtering process, just like what I explained before. You can experience etching process while doing sputtering. So you can have like one step in your recipe which involves etching in a sputtering process. So etch in this case is not like macam wet etch yang kita discuss sebelum ni, tapi it's slightly different. Tapi dia punya konsep sama je. Removing things is called etching, right? So biasing, negative bias relative to the plasma is applied to the wafer, electrically isolated from chamber walls. So in order to see how do you apply biasing, you need to see how do you configure your electrodes, right? For example, in this case, usually RF bias on a substrate, a negative bias, negative 50 to negative 300 volt, DC RF target negative 700 to 2000 volt. Wow, this is very high. Is applied to the substrate. So in this case, the substrate is perhaps silicon, aluminium, glass, for example. So in HDD last time, we used to apply down to on the negative side, down to negative 300. We've never exceeded minus 300 last time. And 300 volt, negative 300 volt is already considered too high for a bias, negative bias. Okay. Sputter etching off and deposition on wafer may occur concurrently. So here is sputter and etch and deposition. So etching and deposition occur concurrently. So if you do apply the bias, then what happens is, if you apply negative bias, plasma is positively charged, argon plus, so it's positively charged. So plasma is all around here in the chamber. So if you apply negative bias to the wafer, apa akan jadi? So it will attract more plasma. So it will attract more argon plus, and it will enhance collision rate or impinging rate of the argon plasma on the substrate. So thereby it will increase the sputtering rate. More and more atoms are going to be dislodged off the target for deposition process. So it's a bit counterintuitive because you are actually doing deposition. Sorry, that one is for the target. If you apply on the substrate side where you want to have the deposition, so while you have plasma colliding on the target to do the sputtering. So for example, you have plasma colliding on the target here on the top side to do the sputtering of ITO, for example. At the same time, you also enhance collision rate of argon plus on the silicon side. For example, if you have substrate, silicon as a substrate, so while you are having your film, ITO film deposited on the silicon, you're also at the same time etching the silicon. So, and this happens concurrently at the same time. So you have ITO being deposited on the silicon, and at the same time you are tuning the morphology of the silicon. So it's not a flat layer because you are inducing more collisions of argon plus on the silicon, creating micro pores or something, or perhaps nanopores. So that will also change, not improve, change the properties of your deposited ITO, for example, right? So there's no hard fast rule whether it's always good to apply bias or not. It depends on what you want to get eventually. So it depends on what properties do you need to measure, and sometimes it may be good, sometimes it may not be good. So we tried last time for hard disk drive. Some conditions are good, some conditions are not good. So, right? So there's no fixed rules. Planarized, the firm as pointed and sloped features are being spotted more easily than horizontal and vertical surfaces. So you may you may use substrate that is already rough, and you might want to polish by etching, can as well. On the other hand, you can also use a planar substrate that you want to induce etching, you want to roughen, can as well. So you may use a combination of both, perhaps. I don't know, maybe some areas are roughened and some areas are planar for certain purposes. There's no fixed rule, can as well, right? So it depends on what you want to get eventually. So bottom line, we use all the fundamentals that we know from the etching, from the plasma, from the biasing, from the magnetron, to do whatever we need to do in the industry. So there's no one way to do it. There's always many ways to do it. So substrate bias again. So substrate bias, resistivity. Well, this one is the properties of the DC and RF bias. You can also, while doing the etching process on the substrate, you can actually induce annealing effect. Okay, bila you induce more collisions of argon plus on the substrate, the what you call the higher collision rate akan menyebabkan momentum transfer, kan, dia akan bagi momentum transfer, dia akan ada heat generated from the collision of argon plus onto the silicon. So that momentum transfer, that collision actually induces annealing process. So annealing maksudnya, ini kita dah belajar last time, you apply heat, you heat up the system up to say 700, 800 degrees C for 1 hour, nitrogen ambient, blah, blah, blah. So that is conventional annealing process. So you can also have annealing effect, not process, but rather effect from the induced collision. So maksudnya you plan to have annealing, but by having etching through the bias. Okay, so that is also another annealing effect. You can help to improve better stack coverage, filling, and stuff like that, right? So that's why I said it's not what we learn is the fundamental, but the way you want to use it can be so wide. Okay, for example, in this case, etching can also be an annealing process. So it's not like etching one process, annealing another process. Conventionally, yes, but in this particular case, annealing is the result of etching. So, right? So advantages of sputtering and disadvantages of sputtering in comparison to evaporation. Advantages is more conformal than evaporative deposition because evaporation is line of sight and sputtering is more conformal. And we've discussed yesterday that sputtering is always in between. So conformality is better than evaporation, but it's worse if you compare to CVD. We're going to learn CVD later on. Better thickness uniformity than evaporation, of course. Compatible with batch processing. That's why it's adopted for mass production. If it's not capable of batch processing, then it will not be capable for mass production. Okay, mass production is all about batch processing. You cannot process like one at a time. Macam kita buat dalam lab, it's not working, right? Because they are counting the throughput, wafer per hour, productivity, capacity per month, capacity per quarter, per annual, and stuff like that. So there's no way to do single wafer processing, right? Easier stoichiometry control than evaporative deposition, yes, can be used for almost any material, unlike CVD. So we're going to see CVD later on. Arriving atoms have higher energies, particularly if you use bias to attract more argon to induce more collision. Disadvantages, subsurface defects can be generated upon impingement of your high energy ions or atoms. So that can also induce defects. So that may need annealing as well. I believe it's not as bad as implantation as far as the energy is concerned. Sputtering and impurity gases are more likely to be incorporated if the energy is too high. not good for epi films, good for polycrystalline and amorphous film. If you wanna talk about epitaxial deposition, which you deposition layer by layer, you have to go for a more sophisticated deposition system. For example, MBE, molecular beam epitaxy, or MOVP, MOVPE, molecular organic vapor phase epitaxy, MOVP. So whatever you see here with E is normally an epitaxial system. So you do layer by layer deposition. So if you compare that to sputtering and evaporation, sputtering and evaporation are more crude. Maksudnya you don't have a very good control of the deposited layer in comparison to epitaxial process. Oh, done. Nanti let me get some information and share with you about epitaxial process. Okay, any questions on sputtering? Anything? I'll start on PD now. Okay, on sputtering so far? Paham semua on sputtering? So far so good or so far not good? Okay, yeah? Okay or not okay? All right, okay then. All right, so let's continue with part 2. So can you see the slides? Nampak kan? Same, right? Okay, part 2 is it'll be on the CVD. So we have discussed in thin film deposition. We've discussed about evaporation. Evaporation can be divided into thermal evaporation, electron beam evaporation. We have discussed about sputtering. Sputtering can be divided into DC sputtering, RF sputtering, and for both, you can also include magnetron into the system to enhance deposition process. So another method that we have is called CVD. So CVD can also be divided into multiple CVDs depending on what have people found or scientists have found during their research. So they alter certain things on the system and they give it a new name and it's published. Then next guys coming into the field trying to do the same thing, and the name is used accordingly until now, right? Okay, let's recap a few things based on the previous materials. So why the vacuum level in the chamber is very critical for film deposition? Why the vacuum level in the chamber is very critical for film deposition? So let's have Naim. Why is it critical? Why is the vacuum level critical for the deposition? Give me a few points. You can unmute or you can type. Okay, Amira, because of plasma. Yes, indirectly, but how? Can you relate a little bit, Amira? You know, unmute pun boleh. How do you get the question to plasma? How do you relate? So bila you jawab, you kena relate the answer or the question to the answer. Mean free path, yes. Okay, mean free path is one. Plasma only form at low pressures, exactly. Yeah, so that's the point. So when you mention about plasma, so you have to come to the pressure first, since the question is about the pressure. So can we have a plasma at atmospheric pressure? Can we have a plasma at atmospheric pressure? Anyone? What do you think, Amira? Since you said that plasma only form at low pressure. Maksudnya at high pressure tak boleh, betul? At atmospheric pressure is not possible? What do you think? Mean free path? Shah, yes. Good. Because we learned last time on the first few pages about the topic. You need to have enough mean free path for the particles to be deposited to travel at least from the material to the substrate for the deposition process, right? So we normally plan the vacuum level to be at least a couple of times longer than the distance, right? So you will have like different mean free path at 10 minus 3, minus 4, minus 5, down to whatever you can go. Not sure. Conventional CVD, we'll see that one. Conventional CVD needs to use low pressure for plasma formation. But we also have now a system that we call APCVD. Saya cakap tadi apa, bila scientists run experiment, they found something, then discover, they come up with a new hardware or something, they change, and then they give it a new name, then dapatlah sistem baru. So in this case, it's called APCVD, atmospheric plasma CVD. So we have a system running plasma at, atmospheric pressure CVD. So we have a system running plasma at atmospheric pressure. But if you want to talk about difficulty of creating plasma at atmospheric versus vacuum, of course, it's going to be a lot harder at atmospheric pressure because you have like particles and moistures and many more things in the ambient that will disturb formation of plasma if you compare to creating plasma in a vacuum system that is free of particles. Okay, so kita akan tengok lagi ya. Second one, deposition. Okay, what else? Any other point for the first question? Why vacuum level is very critical for film deposition? What is another answer that is critical as well? What if you do deposition at a slightly higher pressure, for example? So you have mentioned about mean free path, you have mentioned about formation of plasma. Kalau, for example, this question requires 3 answers, then what would your third point be? What else? What is the another critical point? Film quality, yes, film quality. To be more specific, what is the quality that you're talking about? Yes, no contamination, which is under film quality as well. You don't want to have contamination. So contamination is another thing that you want to include. Kalau ada soalan macam ni, ya. That's why you want to vacuum in the first place, because you want to remove unwanted materials, unwanted particles, residues, moistures, so that your film is very pure. So that kalau you intend to use the film in CMOS, then it's gonna operate successfully as CMOS. Kalau you nak operate as hard disk drive, then it's gonna be a proper function hard disk drive, so on and so forth, right? Describe thermal evaporation process using relevant. Okay, you can go back to schematic. Describe RS sputtering process using relevant. You can go back to the schematic and describe the process. How to solve process issues related to coverage in evaporation and sputtering processes. How do you solve process issues related to coverage? Give me 2 points. What are 2 obvious points, 2 obvious answers that you have to include in your answer? Anyone? Aniza, what do you think? Annealing, yes, good. Annealing is one. You can anneal. You can anneal the sample, for example, in order to improve. How about you, Aniza? One more thing. Or any other? Any other guys? Ladies? Rotate the sample. Yes. 2 obvious answers are annealing and rotation. Done. You can also optimize the mounting, the angle, stuff like that. Can be done as well, but it's not that forward. But the most straightforward is annealing and sample rotation. All right. CVD is chemical vapor deposition. We have learned about physical vapor deposition. This one is chemical vapor deposition, right? Chemical vapor. VD itu sama aja, vapor deposition. Chemical vapor deposition. So it was physical vapor deposition. CVD process, we're going to look into gas phase mass transport. So it's going to involve gas precursors to enable to initiate the process. So we're going to look into growth regimes in the CVD process. We're going to look into a couple of different CVD systems. We have AP-CVD, atmospheric plasma, atmospheric pressure, sorry, atmospheric pressure. Second one, what is LP? What do you think? LP-CVD. It's low pressure CVD, low pressure. PE-CVD, plasma enhanced. How is it plasma enhanced? Let's see. So yeah, if you mention about plasma enhanced, that means the conventional CVD process doesn't use any plasma. And others. Kita ada hot wire CVD, hot wire HWCVD. We also have, I don't know, in publication PA-CVD, plasma assisted CVD. We also have APLP, PE, AP, MOCVD, MOCVD lupa. Metal organic chemical vapor deposition. Ini kita pakai kat Aino untuk buat GaN LED. Right, MOCVD, metal organic CVD. Okay, so what is CVD? So what's actually happening in CVD in comparison to PVD? So it's a deposition process which involves a chemical reaction. So that's why we call it chemical vapor deposition. It involves chemical reaction. In contrast, physical vapor deposition, PVD, there's no chemical reaction. For example, if you want to deposit a thin silicon layer, so remember last time I talked about polysilicon deposition. If you want to relate this back to IC fabrication, layer the MOSFET. So you have gate, source, drain, and this is gate aux. I put it GO, gate aux. Right? So the gate here can be polysilicon. Polysilicon, kita dalam fab kita just panggil poly je. Poly tu usually dalam fab, if you go to the fab, if people say poly, that means polysilicon. Tapi tak sebut habis lah, poly je. So polysilicon deposition. So in that case, the silicon, so in this case, the silicon is not from the wafer, but it's from deposition process. So sebelum ni kita belajar kalau silicon, then usually it's from the ingot and the Czochralski, float zone, wafer, monocrystal, blah, blah, blah. You can also have silicon deposition. So in this case, it can be done by CVD. So if you want to relate to previous methods, you can have electron beam evaporated silicon. You can also have sputtered silicon. You can also have CVD silicon, right? So they are different in terms of the properties. So evaporated silicon is they have different properties, and sputtered silicon are certain properties. CVD silicon are certain properties. So this is called polysilicon deposition. So in this case, in order to use CVD to deposit silicon, you need to use SiH4 or silane. Silane ni lah yang menyebabkan NUS terbakar itu, yang saya pernah share kan. Building fire solar lab tu, solar energy lab, Solar Energy Research Institute of Singapore. Series terbakar and it was down for 5 years and major repair, reinstallation and stuff. It's due to silane punya leakage, right? Silane leakage. To do the silicon deposition for solar cell. So it's a very dangerous gas. So silane, in this CVD process, you're going to have thermal decomposition of the gas. So you're going to have thermal decomposition. So when we say it's thermal decomposition, the process is going to be run at high temperature. Then only you have thermal component. So then that high pressure is going to break the silane into silicon and hydrogen. So you're going to have silicon and hydrogen as the byproduct. So it normally use an open system reactor. Open system is a very simple system. So kita ada quartz kat sini, quartz quartz tube. So this whole thing is quartz tube. Then you have your board, then you have your whatever, silicon or glass or some other stuff that can stand the temperature. Then you can use silane to do silicon deposition. You need to use nitrogen to send the gas into the chamber. You can do ACl as well. You can use hydrogen. You can use phosphine, arsine, diborane for doping. So these one are all dopants. For phosphorus, for arsenic, for boron. Typically we use diborane gas for boron and phosphine for the phosphorus. Okay, so these are all the byproducts of the process. So firm formation involves two stages. The first one is gas phase mass transport of the reactants. So this is the silane that you want to bring to the wafer. So you have thermal decomposition giving silicon deposited on your silicon wafer, for example. Okay. Then the second one is surface chemical reaction in order to enable the silicon formation on the sample. So typical CVD reactors, single wafer or batch process. Typically, if you talk about mass production, then it's a batch process. Kalau maybe single wafer, right? So it uses RF coil or furnace heater to heat the wafers because you need to run the process for like at 1000 degrees C because you need to use thermal decomposition concept in order to break silane into silicon and hydrogen. So these are among the configurations that you can use for your CVD process. So you have your furnace heater, you have your tube. It can be vertical, it can be horizontal like this, right? You can also use RF coil for the heating. Nitrogen or argon can be used as a carrier gas to transport the reactants to the silicon before the deposition can start. Typical process parameters, it specifically depends on which type of CVD reactor we use, but generally there are common parameters like substrate temperature, N2 flow, argon flow, process temperature, and then the flow rate of the gas, process time. So all in all, we normally monitor these three parameters as the CVD, as the output of the process. So we monitor the growth rate, the film thickness, film quality, of course, because that includes defect density as well. So to be more specific, then you need to really look into which system do you use for your deposition. Either it's AP or LP or PE or PA or HW or MO and stuff like that, right? So that will give you different specific parameters for your control. So during the process, there are basically these 7 steps happening. So the first one is transport of reactants by forced convection to the deposition region. So this means, for example, if you talk about silicon deposition, so we are transporting silane to the deposition region since it contains silicon in the gas form. Transport of reactants by diffusion from the main gas stream to the boundary layer. This is where it reaches the surface. Adsorption, not absorption, adsorption of reactants to the wafer surface. So now it starts to be adsorbed before the actual reaction takes place. And then we're going to have surface processes, including chemical decomposition of the silane during the reaction, surface migration to the attachment site. So that means the sites on the silicon that they're going to settle down. Site incorporation, other surface reactions. It depends on whether or not you have substrate temperature and stuff like that. Desorption of byproducts from the surface. So desorption means release of byproducts. For example, if you go back to the equation, they were talking about hydrogen as a byproduct. Transport of byproduct by diffusion through the boundary layer and back to the main gas stream. So we are sending off byproduct, hydrogen in this case, off the tube because it's not needed anyway. So we need to send off the byproduct through the exhaust line, right? So the incoming brings the silane by the nitrogen, for example, and then the reaction takes place in the middle of the tube. And then at the very end of this side, you have exhaust line to suck the byproduct off the system to enable the next deposition. Transport of byproducts by forced convection away from the deposition region. So we're talking about exhaust system to suck. If you, I think you have done have you done any CVD before in your FYP? Anyone? Ada yang pernah buat CVD proses? Dalam no lab ke ada ke? Solid state lab ke? Anybody work with CVD before? Or if you haven't worked with CVD, I think some of you have worked with the annealing chamber, right? Annealing furnace, for example. So if you notice at the annealing furnace, there's at the very end of the furnace, you can see an exhaust line. So exhaust line to exhaust the byproducts of the process, because you don't want them to stay in the chamber or in the furnace, contaminating the next process, for example. So these are the 7 main steps occurring during CVD process. So this is the graphical representation of the steps. Sama aja. So you can see what happens at step number 1. So it's coming in. So your reactants are coming in. Gas phase mass transport of reactants. Number 2, adsorption of reactants. Number 3, so it starts to be incorporated to the surface. Then you have the actual process on the surface. Number 4, desorption of byproducts starts to be released. And then number 5 is number 6 is gas phase mass transport, the byproducts. So the gas stream maintains. So for example, if you use a nitrogen in that case, in order to remove the byproducts. So the reaction here is 2AB gas in the gas form, and then the gas experiences thermal decomposition in CVD process to form solid. For example, if you talk about silane, which breaks down into silicon and then hydrogen. So the gas is the hydrogen here is a byproduct. So you want to have the solid deposited on your substrate. So this is the process again in terms of the mass transport flux, more or less like what we learned last time during Deal growth model, right? So you have flux number 1 as your mass transport flux. Flux number 2, F2, is the reaction flux on what's actually happening on the surface. So the first one is given by the gas phase mass transport coefficient Hg times Cg minus Cs, concentration in the gas form and concentration on the wafer surface, right? So F2 is given by KSCS. Ks is the reaction constant times concentration of the reactants on the wafer surface in order to do the growth. So in terms of processing, you can do a batch process, but normally this is required in mass production. So you can produce either polycrystalline silicon or amorphous silicon. So the quality can be made polycrystalline or it can be made amorphous depending on the process parameters. Temperature of wafers at the same temperature, same growth rate. So you need to ensure that when you run batch processing, the wafers temperature are exactly the same for every single wafer. Right. However, gas phase mass transport regime is required to grow epitaxial. Epitaxial is a little bit more complicated because it is related to the layer by layer deposition. Right. So if you look at this growth rate versus reciprocal of temperature. So normally, if you growth rate on the y-axis and temperature on the upper x-axis, and the reverse of it is the reciprocal is on the bottom side of your x-axis. So if you go for example, if you go for higher temperature, so that means you're going to the left of the x-axis. So that will tend to form a monocrystalline quality of the film. So that means it's epitaxial already. So if you go to the right, if you go to the lower temperature, normally we tend to get polycrystalline film being deposited on the substrate. Okay. So that's how you actually customize the process. So it can be done by temperature, itself. So if you go for the low temperature, you tend to get polycrystalline. If you go for high temperature, you tend to get epitaxial process. But it's going to be at slower growth rate. Epitaxial growth, this is another graph to show about epitaxial growth, right? So temperature on the upper y-axis and reciprocal of temperature of the lower part of the x-axis, on the lower part of the x-axis, and the growth rate on the y-axis. So whether or not you need epitaxial, it depends on the products that you're working on. For example, if you look at this illustration, then dope epitaxial silicon film is usually wanted for bipolar. So some layers you need them to be epitaxial in there, so that's why you have to tune your CVD deposition accordingly. On the other hand, if you can live with polycrystalline or amorphous silicon, for example, if you talk about solar cell, then you don't have to go for epi, you just have to go for poly or amorphous. Then lower temperature is sufficient to complete the process. Okay, this is dope silicon, right? So incorporation of arsine in the deposition. You may have, let me see, what else do we have? Right, out diffusion. Okay, last time we have learned about, let me just finish this and then we're done. We have learned about diffusion of phosphorus and other dopants in silicon. And in fabrication, we also have something that we call out diffusion. Right? Out diffusion is out diffuse certain impurities from your layer to the outside world, maybe to the adjacent layer or something. It's called out diffuse. Out diffusion here, for example, so means doping of the epitaxial film by solid state diffusion from the substrate. You can out diffuse your dopants from the substrate into the epi layer. So for example, if you talk about undoped epi deposition, for example, if you talk about this page, if your epi layer is undoped, you can actually out diffuse dopants from the wafer to the epi layer. So that can be done. So that is out diffusion. So you don't have to introduce any new diffusion process in order to incorporate dopants into the epi, but rather you just take boron or phosphorus from the neighboring region. In this case, it's from the substrate, out diffuse them into the epi layer. Okay. We also have auto-doping, doping of epi film through the gas stream from dopant evaporation from the wafer front or back. So you can have some auto-doping mechanism as well from different regions of the wafer. Okay. So this is how it looks like. Auto-doping processes in an epi reactor. So you can have auto-doping from number one, for example, you can have from the wafer front side. So there, doping there. Number two, from the back side, there, doping there. Number three, from you can also have auto-doping from other wafers as well. How does this happen? You use the gas stream to do the job. Okay, so through the gas stream from the dopant evaporation. So you use the gas to send the dopants to the neighboring wafer, neighboring regions in order to enable auto-doping, right? Concentration decreases with thickness because dopant has more film to diffuse through the to enter the gas phase. Auto-doping at constant level but lower. So, well, this one can be done, but it lacks good control. It lacks good control, right? So you don't know unless you can model the auto-doping process. Normally we process or implantation process, but this is actually happening as well. So we need to be aware that auto-doping may also happen during the process, which could alter the dopant distribution as we discussed last time, right? So last time we discussed about dopant redistribution by thermal budget processes, right? So this is another culprit as well, because it lacks control. So it may change. Yeah, it may change the distribution of the dopants in the wafers. So let's just stop here, and we'll continue Thursday, right? So we continue Thursday. Any questions so far on CVD? I'll try to get some videos for you to see. What did I say just now about the video on which particular area? Something right on the thing I forgot already. Let me recall it on. Okay, any questions? Okay, so far CVD. Okay, all right then. Okay, bye bye. See ya. Assalamualaikum.